Hi all. I'm going to redo the note that I did for section 1.1 yesterday because it was a little bit of a disaster, and I want to get things straightened up. So nothing was wrong from yesterday, it was just a bit scattered and I didn't get everything done that I wanted to do. So I started yesterday by talking about the fact that we're starting our new unit, which is a unit on work, energy, and power, and how it affects society. And I was reminding you that we are finished now officially 2 units in this course, which would be the kinematics unit about motion and the dynamics unit, which is about forces and how they relate to the first unit on motion, right? Using F equals ma, F net equals ma, and then using the A to go back and work with the kinematics that we did in the first unit. I reminded you that we have our sound and waves ISU coming up in 2 weeks, and that we have one last unit after this one, which is going to be electricity and magnetism. This unit here is a lot gentler in math. I think a lot of you will kind of be able to sigh a breath of relief as we work through this unit. There is still quite a bit of math, but it's certainly not as much as we have done in the past. So, like I said, I think you'll find this a lot more gentle. Okay, so this unit is largely about energy. The topic in the textbook is energy in society, and I want to remind you that as a nation, energy is a huge part of Canada. Right? We have resources, we have nuclear, we have, again, we're one of the biggest nuclear countries on the planet. We have lots of nuclear fuel, we produce tremendous nuclear reactors, we generate nuclear medical isotopes for all of North America, and we ship them to Europe, our nuclear medical isotopes. So nuclear is a huge piece. We have tremendous resources underground in terms of fossil fuels, and that is an energy resource for us. We have Niagara Falls, probably when it was built, it was the single biggest hydroelectric generating station on the planet. And we still generate a lot of our power from Niagara Falls, from hydroelectric power. And then we also are working well towards producing new alternative energy sources, being solar, wind, etc. Right. So that tells us that energy as a sector for us as Canadians is a huge sector, which means for you it means jobs, it means opportunities, it means research, it means basically working in different types of settings, and there are opportunities there. And a lot of this unit, again, we're going to be talking a lot about mechanical energy, and again, some of you who are thinking maybe engineering might be thinking mechanical engineering. If you're thinking about civil engineering, you're talking more about dynamics, which we just finished. If you're thinking about nuclear engineering, we'll be doing some of that in part 3 of this unit. So this unit is divided up into 3 parts. Part 1 is about work, energy, power, and society, and there's 5 little subsections, so I'm going to work through each one as 5 separate notes. Okay, so the first one is called work, and work, sometimes called mechanical work, talks a little bit about what's happening to an object, not necessarily to look at it to see that there's a change happening to it, but that there is something going on with it in terms of its ability to do things. So you'll see as I work through this, the concept of work can be a little bit difficult to write maybe a formal definition of it. And I don't really ever like to put a formal definition to work because there's so many different ways to look at it, but I will do that here as we get started. So if you're doing physics, if you're being an engineer, or being a physical science person or an engineering physics person, we talk about work in 2 ways, right? Number one, our basic definition, that for what we call mechanical work, work is done to an object whenever a force is used to move an object to displacement delta D. In other words, you push it, it moves, you did work to it. Okay, pretty simple. Now, I can calculate the amount of work. We're going to use the symbol W for work. We're going to use the applied force here. Again, in Unit 2, we spent the entire unit talking F net. Now we're going to take a deviation away from F net, and we are going to talk about the applied force here, not the F net. Now when we're talking about work being done is measured in, as we can look at our formula here, newtons times meters. So our units here are in newtons. That should be a dot, which is a dot product. It should be down here between the newtons and the meters. Newtons dot meters. And again, just like a newton is a kilogram times a meter divided by seconds squared, using our fundamental units, newton is not a fundamental unit, it's the name of a guy. We did the same thing here. We took the unit, which is a combination of newtons and meters, and we named it after James Joule, again a pioneer and somebody who changed the world of the physical sciences. So James Joule, named spelled Joule. Now, if I'm multiplying force times displacement, what I know about FA is it's a vector quantity. Oops. And I know that delta D is also a vector quantity. So if those two are vector quantities, note that one of the things that we can do with vector quantities is we can add one vector to another. We can subtract one vector to another. I can take a vector quantity and multiply it by a scalar. So just go down here. I can add or subtract vectors. I can multiply or divide vectors by a scalar. In other words, I could take 20 meters per second north and double it to be 40 meters per second north. Or I could divide it by 2 to make it 10 meters per second north. Right? But by dividing my vector by a scalar or multiplying it, I will get a vector answer in the same direction as the direction of the single vector that we're adding. The one thing that we can't do, right, is we cannot multiply vectors unless they're in the same direction. So in this case, if I'm multiplying force, applied force times displacement, which are both vector quantities, right, I can only multiply them if they are in the same direction. And the other part of this, in the same direction is that the result is a scalar answer. So even though force had a direction and displacement had a direction, and they were both in the same direction, work does not have direction. All right, so again, that might be a little bit counterintuitive, but again, in a second-year calculus course, you will probably, maybe even first year, start to figure out the whys of that. Okay, so if I look in the textbook, let me just open up my samples here. Okay, so I've got a couple of samples for section 1.1a. The first one has a person pushing a shopping cart, because it says that the person applies a force, applied force, 25 newtons in the forward direction, pushing the cart in the same direction, 3.5 meters. Right? And the question is, how much mechanical work was done to the grocery cart? How much mechanical work? W. Right, so if I go back to my whiteboard now, if I know that this is a shopping cart here, whoops. If I, come on you. Here's my shopping cart. Here's the applied force in the direction of motion. Okay, applied force in the direction of motion of 25 newtons. And then I have a delta D here of 3.5 meters in the same direction. I can now calculate my work done, my mechanical work, as FA times delta D, which is 25 newtons. times 3.5 meters. And I'm going to get an answer of 88 joules. 88 newtons times meters. But again, we don't use Newton meters. And even though this direction was in the same as this direction, remember, work has no direction. It's a scalar quantity. And my units are not going to be left as 88 Newton meters. We're going to name them after James Joule. Okay, so there's sample number 1. If I scroll down to sample 2, sample 2 says a curler is applying a force of 15 newtons on a curling stone. Let me just pull the question up here. Okay, a curler applies a force 15 newtons on a curling stone, accelerating the stone from rest, V1, to a final speed of 8 meters per second in 3.5 seconds. It says if there is no friction, how much mechanical work was done to the stone. Now, to do that, I'm going to look at sample 2. So here's my curling stone, and it's going to have an applied force of 15 newtons. Boy, it is so hard to write on these iPads. And I know that V1 is from rest, and V2 is going to be 8.0 meters per second, and that the time it takes to accelerate is 3 point, oh, come on. Wait. What's going on with my 3.5 seconds? All right. So, question is, how much work was done to the stone? Now, if we look at our formula for work, it's applied force times distance or displacement. The applied force will be in the same direction as the direction of motion, right? If I'm pushing on the stone to the right of the screen here, it's going to accelerate in the direction to the right of the screen here. So the direction of force is the same as the direction of motion, but I don't know delta D yet. So I go back to my equations of motion from chapter 2, and I learn that delta D equals V1 plus V2 over 2, all times delta T. We didn't use that equation very often, but it was one of our 5. Okay, and if I substitute in here, I get a delta D of 0 plus 8 divided by 2 times 3.5 seconds, and I get a displacement of 14.0 meters. Okay, now I can go back over to here and put in my applied force and my delta D to come up with work. So work is now equal to the 15 newtons of force that's being applied by the curler times a displacement of 14.0, which is 210 Newton meters, or 210 joules. Okay, so there's our two samples for F equals FA times delta D. Now, kind of inherent in that is the notion that if there is no delta D, right, if there's no delta D, then the work is 0. Or if the force is applied to the object in a direction, if the force in the direction of displacement is 0, then there's also, so if the force is 0 in the direction of displacement, then the work will be 0. And you think, well, how can the force be 0 in the direction of motion. If you're pushing it, it's got to be moving that way. Okay, so we'll look at a couple of examples here. And then the other idea here is when I say in the direction, I'm talking about in the plane, right? Within the plane of motion. Which means for one directional motion, I can have positive and negative forces and or displacement. And if they are positive, if they are negative, one's positive and one's negative, then I will have a negative value for work. Whoops. I'll get a negative value for work. Okay, so let's look at an example here. It's 225. Okay, so the first one is the sample for 1.1c. What's going on here? How did I get a split screen? Let's see if this works. Okay, not sure what I did, but anyway, it's gone. Okay, so we were talking about the force. Holy smokes. The force and the displacement in the same plane. Okay, so if I look at the sample for 1.1c, and look at the sample, it says the person is pushing on a car with 300 newtons and it's not moving. So here's the car. Here's the applied force. And we don't even have to do this because we know that if delta D equals 0, then work, which is F delta D, will also be equal to 0 joules. Okay, that's all there is to it. All right, so as soon as I recognize that the force and the displacement are not in the same direction, in this case there's no displacement at all. If I look at the next one, which is the 1.1D, let's move this up. 1.1D, it says shopper is pushing, shopping cart with a horizontal applied force of 41 newtons for 11 meters. The cart experiences a force of friction of 35 newtons. Calculate the total mechanical work done on the cart. So I've got two works being done. I've got a work being done by the shopper, and I've got work being done by the friction. And the two of them are going to combine to do a total sum of work on the cart. Now, let's draw my cart here. So here's my FA. Here's my friction. Okay, so we're not totally out of free body diagrams yet, and we will be after we're done this section that we're doing now. The forward force is 41 newtons. And the reverse force is 35 newtons. And the delta D is 11 meters. Okay, so if I want to know the force from the shopper, the work done by the shopper, I'm going to look at the applied force by the shopper and the delta D. So again, this is the force applied to the cart by the shopper and the delta D of the cart. So I'm only looking at the cart, right? What is the work done to the cart? So the FA is 41 newtons over a displacement of 11 meters in the same direction, and I'm getting a work done of 451 joules. If I look at the B part, it says, what is the work done to the cart by friction? I know the work done is the force, which is 35 newtons, times the displacement of 11 meters. Now notice I've kind of intentionally left some part of my equation out. The 35 is in the opposite direction to the direction of motion. So if my direction of motion, if my positive direction is forward, my force is acting in the negative direction, and I end up with negative work being done to this cart, and I'm getting negative 385 joules. And then lastly, I didn't do this in last night's note, but C says, what is the total mechanical work done? I have to add the work done to the cart by the shopper, plus the work done to the cart by friction. Again, I've never seen this question done this way, because we usually don't ask that. We normally ask how much work was done by the shopper. How much work was done to the cart by friction? Right? We don't usually ask for total work done, right? But total mechanical work here is going to be the sum of the two, which is positive 66 joules. Okay, now that is the work done by the shopper, the work done to the cart by friction, and the total work done to the cart. Right, so those are the three things we need to separate in this question. Right, lastly, if we go back to our note, if the force is being applied at an angle, then I can only apply the component of force that's in the direction of motion of delta D, right? And only that amount of the force, that component of the force parallel to the direction of motion, is all I can use to calculate W. So if I look at a force being applied, let's say I'm pulling a block here, and I'm pulling it this way, which is maybe 30 degrees above the horizontal. Here's the floor. Whoops, that's not the floor. Here's the floor, and the cart's going to get pulled, the box is going to get pulled this way across the floor. Notice that my force in this direction here, okay, so let's say this is a 10 Newton force, 30 degrees above the horizontal. The only force I can use to calculate work done, if this is a 5 kilogram crate, is this component here, which is parallel. So I'm going to use F horizontal is hypotenuse times the cosine of 30 degrees. And now that FH becomes the only part of the applied force that I can use. So notice that in our general formula here, right, it says I'm going to use FA equals cos theta times delta D. Notice if theta was 0 degrees, then cos theta is 1. And then FA cos theta will be FA. So if the applied force is straight ahead, then I'm get to use all the applied force. But as soon as there's an angle there, I have to use cos theta to determine what proportion or what component of the applied force is allowed to be used to do work. Because the part that's up isn't doing any work to the object because it's not going up. Right? There is no displacement in the vertical component or direction, so therefore I have to only use the component that's parallel to the direction of motion. Okay, so I'm going to look at the glass questions here, which are about applied forces that are not in the direction of motion. So I'm going to look at the samples for 1.1b. So I've kind of done it a little bit out of order because I wanted to say this part at an angle to the last part. Okay, so it says, let me go to the question. Samples. Whoops. think I'd learn. 1.1b says that mechanical work done by a custodian on a vacuum is 50 newtons, and it says that the force over here, is this direction, even though the vacuum's going to come this way across the floor. I'm looking at the applied force pulling on the vacuum, which is forward 30 degrees up. So I can only use the component of the force which is parallel to the direction of motion. And I've got a delta D here, which is the direction that the vacuum is going to move. So let's go back to our whiteboard. Okay, so here's the vacuum, square vacuum, and I'm going to apply a force which is 30 degrees above the horizontal, and the applied force is 50 newtons. So to figure out how much force I have here, I have to look at the horizontal component, which is equal to 50 times the cosine of 30 degrees, because I'm talking about the side here which is adjacent to my 30-degree angle. So it's going to be the cosine, and I can calculate that amount. And then I also know that we're pulling this vacuum 3.0 meters across the floor. So if I want to find work is going to be the force horizontal, which is 50 times the cosine of 30 degrees times 3 meters. I'll come up with an answer that is 101.3 times 10 to the 2, 130 joules. Okay, so notice that in the note we actually have come up with a formula that says work is equal to FA cos theta delta D. Right? We can generically use that because, as I said, when FA is parallel to the delta D, then theta will be 0. Theta will be 1. Cos theta will be 1. When theta is 0, cos theta will be 1. Right? And then I get work equals FA times delta D, which is the formula we've been using all along. If I look at the last sample problem here for 1.1b, 1.1b sample 2. Okay, let's go back to the question. It says, oh, I can't even see the question on the screen here. Okay, I can't see the question. It says, a student wears his backpack as he walks forward in the hallway. He walks at a constant velocity of 0.8 meters per second for a distance of 12 meters. How much mechanical work does he do on his backpack? Consider the system diagram shown in figure 5. Okay, so if I look at... Okay, there's no picture here, so I'm going to have to just go ahead and show you what it's going to look like. Cancel. Whiteboard. So here's the student, here's the knapsack. Okay, so again, what I'm looking for is the work that's done to this knapsack. Now notice that the force, so if the student is standing still, right, if the student's standing still, the force that I'm applying to that knapsack is Fg is pulling it down, and if I'm standing, I'm not moving, I'm applying a force in the up direction. Now, let's change the rules here. If I've got the same backpack on my back and I start walking this way, I'm still spending 99.9 or more % of my force is being used to hold that knapsack up. I'm not using it to push the knapsack down the hall, right? It's coming freely, right? There is no friction between the knapsack and really the air, whatever it's going through. There's nothing pushing back on it, so there's no force in the direction of motion. So my only force now is the vertical upward force, while the delta D is the 12 meters of motion going down the hall. they've thrown a red herring at you. They've given you a speed. Speed has absolutely nothing to do with the question. Right? Again, like I said the other day, they might as well be telling you that the guy is wearing I don't know, pair of flip-flops. Right? It's got nothing to do with the question. Okay, so if I now look at this question and try and calculate the work is going to be F, you could say cos theta if you want, times delta D. Cos theta, cos of 90 degrees, is 0. So F cos theta is 0 times delta D becomes 0. Or if I don't even want to use F cos theta and just say, I know that there is 0 force in the direction of motion, and that there's a delta D in the direction of motion, I still come up with a work of 0 joules. So if I say how much work was done to this backpack by the person has done 0 work to that knapsack. You say, that knapsack is heavy. I got a physics textbook in there, I've got a laptop in there, I've got 3 binders in there, right? I got a lunch in there. That's a heavy knapsack, but the force is not in the direction of motion. So I've done 0, and again, if you think about it for a minute, just think about it for a minute, is that knapsack any different now than it was? So here's the knapsack after 12 meters. Taking it down the hall. Okay, is it any different here than it was here? No, it's exactly the same as it was before you started. Well, the same with the vacuum cleaner. I say, no, but the vacuum cleaner moved. There was some friction in the wheels. It had speed. It had kinetic energy, which it didn't have before I started pulling on it. It's very different. Right? And you think, yeah, but the knapsack has speed. But when you're done, the knapsack basically is going to have had nothing done to it. Okay, so there are our sample problems. If I go back to the notes for a moment, there is another section. Okay, so here, so I said to you at the very beginning of this whole note that there are 2 ways to define work. Okay, 2 ways to define work. One was when a force is applied to an object to move it delta D, work is done to that object. Right. The second definition for work, okay, work is done when an object gains or loses energy. So, the other definition for work is equal to a change in energy of the object. Energy is measured in joules. We haven't talked anything energy yet. We're going to be doing that for the next 4 periods, 4 video lessons. And if energy is measured in joules, and I've got E2 minus E1, which is delta E. I've got joules minus joules, and work will be measured in joules, which is what we've been doing all the way along at the top up there. Okay, so 2 definitions for work. Let me go all the way back to the top. Okay, so our first definition here was work is done to an object when a force is used to move an object a distance of delta D. There's definition 1. Okay, and our second definition is work equals delta E. Okay, from there we get into looking at graphs of when a force is applied to move an object. I'm going to skip this section, right? So this section on graphing, we're not going to bother doing that. Now, at the end of section 1.1 in that second document, in the samples and homework document, you'll find a summary. Okay, the summary is there. Let me actually go to the summary quickly. So here's the samples and homework. Oops, samples. There's the summary there. Okay, and again, notice it's a really clear and straightforward summary of what we were talking about in the entire of 1.1 here. Right, so what is mechanical work? How do we use F delta D? F cos theta delta D. Talks about parallel. Talks about we're actually not going to get into that very last piece here. It's true. Oh, hang on one moment. My apologies. Okay, so there's the summary, and then below the summary are some review questions, 1 to 9. 9 is graphing, so you can skip question 9. Right, but the rest I think should be fairly straightforward, talking about force, displacement, and work done. Now, lastly, if you go back to my notes here, you'll see that in our textbook, there are a number of questions also. So our textbook is the Irwin textbook. That's the one with the sky border on the front